colors.
Good morning, everyone. Thank you all for coming. Damian will be giving us a further lecture on the SYK model. Thank you again for the London Institute of Political Science for hosting us, and Damian, thank you very much.
Thanks, everyone. Welcome again. Good morning. So, third lecture. Good to still have people to hear me. Yeah, the good thing about this is that if you miss any of the previous lectures, that's fine, because I will talk about something completely different. And we will see in the end how everything connects to each other. I was talking about two-dimensional gravity in our previous lectures. And today I will talk about this SYK, such the Kitaev model, that is a quantum mechanical model of fermions, Majorana fermions. And yeah, we'll see how that is related to gravity at the end of the lecture. Maybe a bit longer than previous lectures, so just stay with me. Be patient. Everything will appear. So as always, we have three main objectives for today. The first one is just to define and study the SYK model. After we know what we are talking about, we will compute 2-point functions in the large n limit. So there will be n fermions in our model, and interesting things will start happening when the number of these Majorana fermions is large. And by the end of today, I hope to get to a point where we can look in the IR sector of the theory and see how the Schwarzian emerges. Okay. As always, feel free to ask questions, interrupt me. Yeah, the last two lectures were more about gravity. This will go back to quantum mechanics and a little bit of quantum field theory. And Nikolai Gromov already recorded a very nice lecture on Mathematica that should be already online somewhere in the integrability. I think it's in the Integrability Journal Club channel, but I will put, yeah, and, it's somewhere on YouTube. So many of the things that I will be explaining, especially in the first part of the lecture, are demonstrated in Mathematica by Nikolai, and he shows all the tricks on how to do these calculations without getting stuck forever. The trick of all this is that, yeah, in the large n limit, the representations of the fermions in the SYK model grow exponentially in size, and very soon the computer just gets stuck. But there are tricks for that. And moreover, we will see today that there are many corners of the model where we can use analytic expressions and solve the model without having to go to the computer. So that's fine. Okay, so that's the plan for today. And let's get started. I also put the lecture notes for these three lectures. They will appear somewhere on the website during this week. And they all include, in the end, some homework problems. So if you want to work on the things I've been telling you these last weeks, go there. Feel free to try to answer all those and then ask me if you have questions or anything. Okay, so Majorana fermions is our first point of the day. They will be our main characters in all this story. I will call them psi, and as I've been telling you, there will be n of them, so I will run from 1 to big N. The condition that they are Majorana means that if I dagger these fermions, I get back the original fermion. And they are fermions, so they anti-commute. So these are the anti-commutation relations, and yeah, ij go from 1 to n. This is known as the Clifford algebra, and Clifford has a nice story that I read yesterday on Wikipedia. He was a student at King's. He started the university at the age of 15. Then he moved to Cambridge. And then I don't know what happened with his life, but he decided to study these algebras. He had all these amazing results. And then at the age of 33, he died. That's Clifford, and that's the algebra we will be studying today. Well, in 33 years, he did more than I'm 34. I don't have any Galante algebra.
It's threaded that the boat crashed at some point also.
Yeah, he survived some. That as well.
A shipwreck.
A shipwreck. He survived that. Then yeah, he was a bit crazy, so he used to go to Portugal to like relax. And one time he was there and he never came back. He was member of the London Mathematical Society, fellow of the Royal Society, all these fancy things that are here in London. And he gave us the Clifford algebras. I think it's a nice story. Anyways, we need to find the n-dimensional representations. We will work in Euclidean signatures. We've been working in all these lectures. And so the easiest way of finding some kind of a Hilbert space for this is to define some nicer fermions that have the usual anti-commutation relations of fermions. So we can define sums of these Majorana fermions and CI dagger. And now I here runs from 1 to k, and I will assume for now, because it's easier, that n is even. So n is equal to 2k. If n is odd, well, you need to add one extra. Yeah, it's a bit more problematic, and in any case, we'll take the large n limit, so it won't be very important. So now, first homework of the day, check that these C's do obey the usual anti-commutation relations for fermions. And now Cj dagger is equal to delta ij. And if we have these anti-commutation relations, now we know how to build the basis for our Hilbert space. We choose some vacuum state that is annihilated by all the C's. And then all the possible things that we can add over here are just CI daggers. So for each of these daggers, we can have some number and n. N1, switch dagger n2, etc. And because of this, the only n's that are allowed in this sum is ni equals just to 0 or 1. So there's only one or no fermion there. And so this is a basis. This will be a basis for this n-dimensional representation of this Clifford algebra. And yeah, now we can count how many states has this basis, and it just for each case we have either 0 or 1, so the total dimension is equal to 2 to the n over 2 or 2 to the k, because we have k of these c's. And we already see that the dimension of the Hilbert space goes like 2 to the n. So when you start putting n equal to 20, 30, depending on your laptop, you'll die. Okay, so this is great. And so from this computational perspective, at least, we can build them recursively, starting by the k equals to 2 or the n equals to k equals to 1, n equals to 2 representation that you probably know what types of matrices obey this anti-commutation relationship. Anyone? Except the ones that already know the answer. We can start with gamma, with the sigma matrices, and then build from there the n-dimensional representation. So homework number 2, check that these two matrices, I think Nikolai will do that during the first 30 seconds of his mathematical talk. So you can check that these two matrices obey this anti-commutation relation, and then for any given k, you take the last one and you build the next one by doing this. And again, homework, you will need to show that these obey that anti-commutation relation. K minus 1, and you tensor it. I mean, yeah, so I here will go from 1 to n minus 2, and these are all built from the k minus 1 representation. And then I need to add the 2 extra fermions for the k1, and this will be given by, so I have here the identity. Yes.
It's the first matrix that you wrote length
Which one? Yes, this one is phi 1. So we have k equal to 1, n equals to 2, and there are 2 matrices. And for any k, we have this. So we start with these ones, we plug them for the k equal to 2, so that will be n equals to 4. We put those 2 matrices over here, we get 2 fermions, then we add these 2 ones, and we get the 4 fermions of the 4-dimensional representation. And so you can see from here that so each fermion is 2 to the n over 2 times 2 to the n over 2 matrix. And I computed the 4x4 dimensional matrices, but I'm not going to write them down. So you can check the notes. And you can try to do this loop in Mathematica to create your n representation and see how far you can get until Mathematica just crashes. It will probably be around between 20 and 30. Okay. So this will be our main characters in this story. They will be big matrices with some numbers that anti-commute. Those are Majorana fermions, to demystify a little bit. And so now, okay, if I don't do anything, they will be just free, hanging there, some matrices that with some numbers. But now I will specify a Hamiltonian for these matrices. And with that Hamiltonian, they will start interacting, and we will study that model. Okay, good. So the SYK Hamiltonian, well, let me just write it like this. We will take 4 of these fermions. Psi I, psi j, psi k, psi l, and we will multiply them as we multiply matrices. So this will be a multiplication of 4 2 to the n over 2 by 2 to the n over 2 matrices, and they will give another 2 to the n over 2 by 2 to the n over 2 matrix. So the Hamiltonian is also a 2 to the n over 2 times 2 to the n over 2 matrix. I'm just saying this many times, just to make clear that we are dealing with very large matrices from the very beginning. And what we will do is something a little bit strange, but interesting, that is taking all possible groups of 4 fermions. So we will sum over I, j, k, l from 1 to n. These are called all-to-all interactions. And each of these interactions will interact with some coupling that I will call J. And I will put here I, j, k, l. And this is our SYK Hamiltonian. So a little bit how to imagine this. So everything happens at one dot in space. But let's assume that we can zoom it, and then we see the fermions somewhere hanging in this dot. And then the idea is that, okay, I take groups of 4. So 1, 2, 3, 4. And, well, okay. They interact with this J, I, J, K, L. Then I take another group of 4. And they also interact with some different Ji, Jkl, and like that with all possible groups of 4. So exercise number 4, I guess, is show that we need n factorial over n minus 4 factorial times 4 factorial couplings. So this sum is a little bit degenerate because this psi's anti-commute. So there's only this number of independent couplings in the theory. And again, if you take the large n limit, this scales as n to the 4th power in this case. And this is a power law. It's still bad when n is large, but not as bad as exponential. So the problem will not be choosing the couplings in this case. Okay. So we have our multiplication of these 4 fermions. We put these numbers over here, and then we sum over all these. So the end point is some big matrix that we call the SYK Hamiltonian. And the only thing that I'm missing is to tell you how to choose these couplings. So far, I've been telling you, okay, there's a number that has to go here, but we will choose these numbers to appear in a very particular way. And so couplings will be chosen randomly. From a Gaussian distribution with 0 mean and variance given by sigma. There will be some normalization over here that we don't care. There will be a capital J with no indices that will be important, and a very particular scaling with n. And this will be key for our analysis. So J is one number. It comes from this Jij, so it has dimensions of energy. It's dimensionful. And it's fixed. Once we fix that J and N, then we will have some Gaussian distribution for our JIJKLs. And we will start picking them randomly with more probability of getting values around here and less probability of having values over here. And so once we fix N and J, we have this Gaussian distribution of couplings, and then we choose randomly n factorial over n minus 4 factorial of those, and that fixes one particular realization of this model, and we can work with that Hamiltonian and solve the theory. So this number over here is just normalization. It's not very important. But the fact that n appears over here and with a very particular power will be important to have a well-behaved large n limit. So when we take n to be large, we want that n there with that specific power to have a well-defined large n limit that is not 0 or infinity, but it gives some finite interesting piece.
Is sigma the variance or the standard deviation?
It's the variance, the variance minus x squared over sigma squared. I don't know. In principle, you will have like an x naught over here, but this we are setting to 0, and then sigma. Other questions? Okay, and so now you can complain that I'm choosing some couplings randomly, so why should I care about this particular realization of SYK, and why shouldn't I take some other set of JIJKLs to analyze my theory? And then a little bit to answer that, what we will be doing is to average over all possible realizations of this model. So So yeah, so well, yeah, let me write it down. So I first choose a set of these couplings. I compute whatever I want to compute. Then I choose a different set of couplings. I compute again. I save that result. And I keep doing that until I average over all possible choices of these couplings. And then I can average over all the results. So this is quite crazy. But computationally, and this is in part, well, I think Collier will only do one realization of this, so you should repeat what's in that Mathematica file many times to get an average answer. But computationally, so you choose first some random couplings. Then we compute. And then we choose a different set. And we repeat all this many times. And the last step is to average over all possible realizations. And okay, this is not quite what we do in high energy physics, where we have a given action and fixed couplings, and we study that model, and it's usually already quite hard. But this is usually what happens in, well, very complicated models where you have so many couplings that and so many interactions that it's very hard to model them. So you just say, okay, what happens if they are all random? We average over all of them, and we get some results. And historically, there have been examples where this thing that looks quite crazy worked quite well, even to describe things that happen in nature, like the energy spectrum of heavy nuclei. But that's a whole story that, well, I can tell you some other day. It's very interesting, but this is something that people do in disorder systems a lot, but that we are not very used, and maybe that's why it came from, the model came from people from condensed matter rather than from a high energy perspective. So this is what we want to do.
Sorry.
Yes. Yes, let me just say it again. So the Gaussian distribution is used to pick these JIJKLs. I choose this n factorial of them, and I get one Hamiltonian. With that, I can compute, say, I want to compute a two-point function, so I do e to the minus h tau psi I 0, e to the h tau psi, something like this. And I get one result for one realization of the model. Now, okay, I save this in my memory, and I say, okay, now let's go again and pick some other set of numbers that I take again from that Gaussian distribution. I get a different Hamiltonian because all these numbers are different, and I compute this again, and I save that number. And I do that infinite times, and eventually I sum over all of them, divide by the number that I computed, and I get an average over all possible J's.
The average is with uniform weight.
Yeah. Other questions? So I described this procedure, but you need to be a little bit cautious about it. And the problem appears when we start trying to compute things like, well, what we computed last time in gravity was the free energy that was given by the logarithm of the partition function. So say that we want to compute log z at some temperature beta, inverse temperature beta. And so now you can ask, how do I compute this thing over here? there are in principle, well, this thing over here, no, but I want an average over all possible realizations of this model. So I need to put some averages over here. And there are two ways I can do that. One is average over here. So this is like what I was describing. You compute the 2-point function, you save the number of the 2-point function, and then you average over all 2-point functions. Or you can do something different, that is first average over the partition function, and then take the logarithm. And if you think a little bit about this, there's no reason why these two things should be the same. This is what people call annealed disorder. And when you try to compute this, there's something that you might have heard about that is called the replica trick. So what you need to do is to consider many copies of the model, and in order, well, okay, so taking the log is hard. So instead of taking the log, we take powers of Z. But it's usually a hard procedure, and it's maybe a bit a posteriori result, but in SYK, up to order 1 over n, both approaches coincide. At least in the large n limit to order 1 over n. So yeah, it's kind of a problem that people in disorder systems study a lot, especially what happens when, well, there's some symmetry between replicas that is broken, and there are glassy faces, blah, blah, blah. But at least for our simple SYK model, none of this happens, at least at order 1 over n, and we are fine with doing our simple annealed disorder.
Sorry, what do you mean when you say they coincide at 1 over n?
That if you compute this and you compute this, when you take the number of fermions to be very large, they coincide. Okay, and finally, one extra thing that we can do is instead of having 4 fermions here, we can add as many fermions as we can, 1, y, 4. And so we will have an SYK Q model where we will put Q of these fermions. So what I was showing before was the Q equals 4 model, but in principle I can have Q of these, IQ, and I can sum from I1 to IQ from 1 to n. And now sigma will have to scale as j over n to the q minus 1 over 2. And when you put q equals to 4, you get back that result. And here is some number that I don't care about. Okay, and there's some extra thing that I need to do is that if I want to keep the Hamiltonian Hermitian, I need to put I to the q over 2 over here. Okay, and different things happen depending on this number q. One interesting example is the q equals to 2 model. So in this case, this thing just is m ij, psi I, psi j. So this works as a random mass term for the Hamiltonian. There are no interaction, it's just random masses. And we will see that it has a very different spectrum to the rest of the Qs. All the other Qs share similar features in terms of the energy distribution of these Hamiltonians, but there's an extra thing, nice limit that happens when Q goes to infinity. And so when n goes to infinity and then Q goes to infinity, the system can be solved analytically for all j's. That's the important part. Okay, so let's keep pushing a little bit this description of fermions as matrices. One thing you can do is go to Mathematica, just tell Mathematica to choose these random couplings for you. Nikolai will be showing that in his video. And then you can choose, for instance, a Q equals to 2 model, a Q equals to 4 model. And once you have the Hamiltonian, you can just diagonalize that and find the set of eigenvalues of this Hamiltonian that will be our eigenenergies. And then you can make a plot showing how many energies you have at a given set of delta E, like a histogram. And so let me just try to show you what you get for the different Qs, and then you see the nice plots in Nikolai's lecture. So energy spectrum. So you do any Q greater than 2, and what you will get is an energy spectrum that looks more or less like this. So it's similar to a famous semicircle that appears in random theories. And the interesting thing about this is that if we look at the lowest energy, so this is energy. If we look at the lowest energy and we look very close to this ground state energy, we see that the plot goes up like crazy, and we find many states hanging very close to the ground state energy, E naught. And this is typical of random matrices. If you see how this scales with n, you will see that rho of E scales like E to the S naught times n. And what you see, this is for a fixed n, the semicircle is for a fixed n, so what you see here is some kind of root epsilon. But if you compare for different n's, you will see that there's an exponentially large number of states hanging very close to the ground state. Yeah. Sorry. Rho E to the S naught n times root E. Something like this. Where S naught is some number. Yeah. No. That you can play with in Mathematica. You will get in the large n limit. It will approach the semicircle very well, but in principle you will have you will have to choose some delta E, and then you will have blocks with delta E over here, and this will be something like this. You can do it in Mathematica, and you will see it will be something. Wow. And it kind of approaches this line when n gets large enough. Yeah, you can play with this delta E and with N in mathematics and see when you get this nice description. And this is typical of these chaotic systems. I don't want to say a lot about that, but we will see more next time. If we do Q equals to 2 instead, what we get is that there's a very long tail with very little states. So if here we have our ground state over here, you see that this doesn't very close to E0. This doesn't grow, and it just there are very small number of states lying here close to the ground state. So there's nothing very interesting happening at very low energies. While here, all of a sudden, we get a lot of different states that can interact.
Sorry.
Yes. This? Some number. Yeah. I don't want to say anything more than just some number. More questions?
What's in the y-axis?
Number of eigenvectors with this energy. So yeah, you have your SYK Hamiltonian. You diagonalize. You get a list of 2 to the n numbers, and you say how many I have between the minimum number and delta E, and that's the number I'm plotting over here. It's a histogram. More questions? Okay, so we will be interested more in this case, but you can check and play with it in Mathematica. And the other thing is that, okay, if you just do one realization of this model, this plot will be quite dirty, especially over here. But if you average over all possible realizations of this, it will start getting smoother and smoother.
So is the Q equals to plot unboundable energy?
About you mean over here?
Yeah.
No, they all have one ground state energy. But the point is to see how many states you have close to that ground state energy. At finite n, they all have only one ground state energy, or yeah.
So that distribution is average. It's computed through that procedure.
You can play with it. There's an interesting property about this model that it's kind of self-averaging. So for many quantities that you can compute, the result of doing one realization of the model is very close to the one you get by doing many, many realizations of it. And so you will get this plot even by doing one realization. The only thing I'm saying is that when you do many of them, you will get a smoother plot where the noise that you have usually over here will be kind of it will go away as you increase the number of realizations. But for this type of simple observables, one realization of the model gives qualitatively the same result as the average of all of them. Okay, and one last comment about this more computational approach is that, well, once we have the Hamiltonian and once we diagonalize that Hamiltonian, we have everything we need to compute whatever quantity we want. So say now that we want to compute, well, this is kind of what I was writing before, but say you want to compute the 2-point function of these fermions at some Euclidean time t, an inverse temperature beta. You know what you need to do. You just need to multiply many matrices together. So e to the tau h, psi I, e minus tau h, psi I. And then to get the thermal expectation value, we multiply by e to the minus beta h. And we take a trace of all these matrices. And that's it. And sometimes we want to normalize this by the trace of e to the minus beta h. And if we want to compute the expectation value, an average over j's, we just repeat this exercise many times and compute the average over j's. And that's it. We have our computation. You can put that in Mathematica, and you will get an answer. Questions? Can already be condensed matter physicist if you don't have questions. That's it. Yeah,
Are these plots independent of the choice of n?
Good question. These plots become more and more independent of n as n goes to infinity. So there will be a nice behavior when n is very large, and you will start seeing this in the computer when n is 20, 25, 26, 30. If n is very small, there are not enough eigenvalues to play with it. But you can do this computation for many values of n and start seeing how the solution approaches one solution that looks kind of independent of it. Probably you want to sum here over n and put a 1 over n here to have something more or less properly defined. But you will see that as you increase n, you will get some result that is kind of independent of n. Yeah, good question. More? Okay. Good. So now I will change the approach a little bit and we'll treat this theory as high energy physicists. So I will take this this theory, write an action for it, and compute either Feynman diagrams or a path integral and see how this large n behavior appears in this. So second point of the day, solving the SYK model at large n. The conclusion of this first part is that the SYK model is just a model of big matrices that we multiply them, we diagonalize them, but it's nothing more than that. It's a set of matrices living at a point, interacting all to all with some crazy couplings. Okay, we average over many realizations of the model, and there's interesting things that start appearing when we take the large n limit of this. But we can go, a little bit farther and try to solve the model analytically at large n. And for that, we would like to define, instead of a Hamiltonian, I will write an action for this SYK model. As I told you, well, we will stay in Euclidean signature, so, and everything happens at a point. So this is 0 plus 1 D system. And the action for this will be just given by some kinetic term for these fermions, psi I, d tau, psi I. And then our SYK Hamiltonian will appear here. I, J, K, L. Plus, and this sum is overall IJKs. And
Are we back to Q is equal to 4?
are we back to?
We're back to Q is equal to 4.
For now, yeah, I will just because just to have one to write down. I will just pick Q equals 4, but I will tell you the final results. I will tell you how they depend on Q, and then you can repeat the calculation. And so this will be one realization of the model, but in principle, as I was telling you, we will be interested in averaging over all possible realizations. And then the way we do this is to integrate over all possible I, j, k, l's with this Gaussian distribution, j, I, j, k, l squared. And here I will have this sigma that was j squared over n cubed. And then I will have my path integral over fermions with e to the minus s SYK. Okay, so there are two ways of getting this number or using this number to compute a two-point function. One is to start solving these equations. That's something we will do maybe in the second half. How am I doing? It's hard to read this thing. Yeah, I should be, well, okay, running way behind. But I will try to sketch that computation because I think it's a nice calculation to do from the path integral perspective. But just to start having a feeling on what's going on, I will try some perturbative calculation. So perturbations or diagrammatics, people call it in different ways. Just if you have that action, how to compute Feynman diagrams. So we can start putting j equals to 0. And when j equals to 0, then h is equal to 0. There's nothing going on. The fermions are just independent of time. 0. And we can compute the two-point function because we know that psi I, psi j is equal to delta ij. So if we want to compute the two-point function jij of the free theory at some time t, well, yeah, it will be the time order two-point function. So yeah, if t is greater than t prime, well, anyways, you understand what I'm saying. You will get 1/2 delta ij coming from this, and then you will have the sign of tau just to have a time order two-point function. And then again, we usually don't care about one single two-point function, but we like to sum over all fermions, and then you get a free two-point function as a function of tau, that is 1 over n, sum from 1 to n, because here there's a delta function, you only need to sum diagonal components of this. And then you just get a sine of tau over 2. And it's antisymmetric because we are talking about fermions, so there's the sign of t over there. And it's just, yeah, 1/2.
When you say j is equal to 0, do you mean the coupling rather than the term that appears?
Well, I'm saying the term that appears in the variance, that's 0. So that basically means that all the ji, jkls will be 0 with a probability 1, right? So if the variance, how is it? Yeah, if the variance goes to 0, then this gets kind of picked like this, right? Your Gaussian distribution, if sigma goes to 0, gets very, very thin. Yes.
You not just get like a standard normal distribution.
No, you get a peak, right? So sigma is the size, the width of this normal distribution. So as sigma goes to 0, this gets very thin, and so all your Ji, jkls will be chosen from only 0 with a 1 possibility. So they are all 0. Well, and just for completeness, and because we might need it afterwards, it's usually nice to go to frequency space. And so if we do J, ij free as a function of omega instead of tau, we do a Fourier transform of this, and we get minus delta ij over I omega. And this is nice because in Fourier space, we will see that our equations will simplify quite a lot. Okay, so we have our free propagator, and now we can look at the vertices of this theory. So now let's say that we turn on a small j, and on top of the free propagator, we have this vertex with 4 fermions. So it will be something like this, with legs that will have I, j, k, l. And then we have our free propagator, G free. But we still haven't incorporated the average over disorder. And the way this can be done in this diagrammatic expansion is by adding a field that will be J, treating J as a field, but it doesn't have any free propagator. There's no kinetic term for J. It will be just a term that can appear with a 2-point function that will be given by J I1, J1, K1, L1, J I2, G2, K2, L2 equal to J square over N cube and all the deltas. So delta I1, I2, delta J1, J2, delta K1, K2, delta L1, L2. Okay, so basically we will be looking at diagrams that will have these 4 vertices, and we'll have an extra leg over here that will connect to some other vertex like this. And there will be only 2-point functions for this. The 1-point function is 0. And that's the way we will include this disorder or averaging over possible realizations in our diagrammatic expansion. Is clear? Okay. So now let's start doing Feynman diagrams. So we said already that at 0th order, we have, well, so we want to compute some, well, we will call it directly G. So we are looking at some renormalized 2-point function. The leading order will be just the free propagator. And then we will start looking at things that are proportional to J. But diagrams that are proportional to J will have, well, will be some kind of tadpole diagrams that will have the J running like this. but because expectation value or the 1-point function of J is just 0, all these types of diagrams will not appear in our sum. And so we need to go to second order in J to find the first non-trivial diagram. Okay, so let's look at the first non-trivial diagram. We'll have 2 vertices. They will be connected like this. So each vertex has 1, 2, 3, 4, 1, 2, 3, 4. We are fine. And then there will be this J disorder over here. Oh, so the way I write it down, so okay. Yeah. What I was meaning is that if we want to compute average over J's of this diagram, this is the same as writing this down. Is this clear? This is a bit different from what we are used to. And now we can compute.
You need to have dotted thing once, or would you need to add more of them? You got a sum of you have 1, 2, 3 as usual, or do you need only 1?
1, 2, 3. You mean if I?
J to J. Yes.
Well, the only thing, well, J will only have a 2-point function. So I will only need to add 1 J line in between two dots, and then it's all weak rotations, nothing more than that. But if I have more vertices, then I can have, yeah, we will go to that. But if I just keep to order J squared, that this is the diagram that I'm doing now, this is the only reasonable, well, the only non-vanishing diagram at least. Okay, and we can compute this diagram. It's a mess, but so there will be 3 free propagators over here, and then you will have this J squared over n cubed term, and you will have all the delta functions that will contract the indices over this part and this part, this part and this part and this part and this part. Sorry, I'm going a bit fast over here because next one I will do it with a little more detail, and then I will get lost and I will need your help. But what you get over here is J squared over n cubed. And then you get J, say I put I, J, K indices over these legs. Then I will get JII, J, JJ, and J, KK. Free, oops, free, and free. But here I'm summing over I, J, and K. So basically, what will appear over here will be some J squared over n cubed times n cubed of what I called G3. And n cubed cancels with n cubed, and that's the reason we put sigma with this particular power n, because now this diagram, when n goes to infinity, this scales as n to the 0. So it gives a finite contribution to the diagrammatic expansion. Okay, I see the blackboard and it looks like a mess. So let me erase all this and let me just. Yeah.
Why do we have only one G3?
No, cubed, sorry. And there will be some delta function of these 3 legs. So there will be a delta I1, I2. Yeah, sorry. More questions?
What do the delta come from?
This one, well, you need to do the, yeah, you need to do the diagram carefully, but this J, this 2-point function of J comes with 4 delta functions of the four legs. So you will have delta functions connecting this index with this one with this one, this one with this one, and this one with this one. And that's the extra. So all these are contracted in the end, and you are left with one free delta function.
Isn't there an integral left to do?
Yes. I'm just looking at the
scale.
The scaling with n. That will be the interesting part. This will be very schematic, and that's why I like to do the path integral afterwards, because then there's no doubt about how to compute diagrams, which one contribute, which one no. But you will see that some nice structure will appear. I think I'm out of time, so I will leave as an exercise the next. So let's go to J to the 4th power now. Let's look first at this diagram. So one is the one that we had before. There's a disordered line over here. And then what we can do is to add 2 extra vertices over here and do another of these balls with the disorder appearing over here. And I wrote with some detail this diagram in the notes, so you can take a look afterwards. It looks more or less like this. There are lots of delta functions all the time. But you can check that this diagram goes like J to the 4th over n6. That part is simple because it's just these two lines over here. And then you have 1, 2, 3, 4, 5, 6, 7. No. In the end you get 6 free propagators. So I think this one is contracting with this one. And so if you do the calculation properly, you get GII free 6 times. And so again, this I'm summing over n. I will have n of these. So I will write G to the 4th and 6, G free to the 6th. And here I have n to the 6th. And so this again is an J to the 4th, n to the 0th power diagram. So it will contribute in the large n limit. But with 4 vertices, you will have many, many other diagrams. And you will have to believe me or do the homework to see that those are subleading in n. So for instance, you can have something like this. It's the same diagram, but we can choose to contract these legs in a different way. So for instance, we can do like this. And because the 2-point function comes with all these delta functions, you see how they are contracted, and you can check that this term, for instance, goes like J to the 4th over n squared. So the contribution of this diagram goes to 0 as n goes to infinity. And you can think of many other diagrams with 4 vertices, something like this maybe, with the disorder running over here, or, well, many other diagrams. And they are all suppressed in the n going to infinity limit. And so one can show that basically this computation over here, when we take n to infinity, is restricted to these types of diagrams that we call melonic diagrams. Don't ask me why. And so in the large n limit, so now we are taking n to infinity. This sum reduces to the sum of, well, okay, we have this one, melon, the one with 2 melons. We have 4 vertices, and here I will put 3 and 4 and 5. And then we have corrections to this one coming at higher loops by doing the melon of the melon with the right construction of the disorder, plus. And so here comes the nice part of it. So if we define the sum of all these columns in some sense as sigma, what people call the self-energy of the particle, and it's defined as having like a melon, but with G on each leg. So it's, yeah, well, it is what it is. Then this sum can be written as, I mean, you will need to think about it carefully. But this 2-point function will be written like the free thing plus sigma plus sigma sigma plus, well, you get it. And this is only valid in the large n limit. Okay, I'm collecting all these diagrams in this sigma, and then I'm doing this sum, assuming that this will get corrected with this, and like that. So when I put G here, it's kind of all these renormalized 2-point function. I never completely understood these two equations, so it's okay if you don't understand it either. And that's why I like doing the path integral afterwards, because it gives the same equations and it takes care of the large n in a very nice way. But at least by looking at these diagrams, you can have a sense of what's going on. Large amount of diagrams that contribute at, say, j to the 4th with 4 vertices. Only 2 of them contribute in the large n limit. And this big reduction of vertices make it possible to write down the whole expansion up to infinite, up to j to the nth power, just as this sum over here that we will sum in a minute, and we will get closed equations for any value of the coupling. Yep. So yeah, so G will be a function of tau 1 and tau 2, and sigma will be a function of tau 1 and tau 2. And so we will sometimes treat these numbers as matrix indices, but continuous matrix indices. And so when we multiply these things, so A times B, this will mean sometimes the tau prime of A tau prime, B tau prime, tau 2 prime. And this A times B will depend on T and T prime prime. This won't be super important for us right now. Okay, and let me do this sum, and then we make a break, because I can see terms at large n for any value of the coupling. And this is, yeah, quite impressive. It's not something that happens very usually in quantum field theory or in quantum theory in general. Okay, so let's do this sum, and then we make a break. So let's write down this line over here. Well, first, let's do the simple one. So phi equals to j squared g cubed. And now we need to do this one. So this one is g is equal to, first we have the free propagator. Then we have g free sigma g free. Then we have g, and I will stop writing the freeze because it will take me too long. Sigma g free plus plus plus. So now we can take the first g free out and see that this is a geometric sum. And we can sum a geometric sum. So this gives g free 1 plus sigma g free to the minus 1. And if we put this the g inside the parentheses, then we get our, yes. Is there a question?
Would it be 1 minus sigma?
1 minus sigma, yes. Yeah, so why I put a plus here, I don't know. Sorry, minus. So then what we get here is g free to the minus 1 minus sigma, everything to minus 1. And these are basically our Schwinger-Dyson equations. So g free, we computed it before. It was a delta function of t minus t prime times dt, or dt prime. And we usually don't put all these things in there, and we just write g is equal to dt minus sigma to the minus 1, and sigma is equal to j squared g cubed. And this is the big result of the day. So what did we do? We wrote an action for SYK. We included the disorder. We treated the disorder as an extra field that does not propagate freely, but only goes in between vertices and has a 2-point function given by the variance of our probability distribution. And with that, we computed Feynman diagrams. We saw that out of all the Feynman diagrams that can appear at a given order, the only ones that contribute are the ones that are these melonic diagrams. And so then we managed to write the full 2-point function for any value of j as an infinite sum over all these diagrams. And even more, we managed to do that sum, and we found a set of equations that are valid for any value of j. We sum from the linear term up to j to whatever power, that are valid only in the large n limit. So in the large n limit, we can solve the theory completely by solving these equations that are called Schwinger-Dyson equations. And again, the important thing is that there's a j square here, and this is valid for any value of j. It can be 0.001 or it can be 10. And Kolya in his video will show us that not only that we have equations like this that we usually don't, but also these equations are very nice for putting it in a computer and getting a numerical answer by doing some recursive algorithm in Fourier space. So that's in the video that Kolya just uploaded to YouTube. And you put it in Mathematica. You work out a little bit the details, but you end up with a solution for G, so a 2-point function for any value of J that you would like. And in particular, you can try to plot G at some given time as a function of the coupling and see how it changes from the free theory that is just the sign function to something more interesting happening at strong coupling. Questions? If you don't trust all these diagrams, what I'm planning to do next is to take the full path integral and start integrating everything out. The theory is quadratic well, we will see, but the fermions will start appearing quadratically, and even though there is no explicit n over here, only in the limits of these sums, n will start appearing in the path integral, and in the large n limit, we will be able to do a saddle point approximation that will give us this same Schwinger-Dyson equations. So you will trust these diagrams a little bit more.
Why is G3 that delta with the derivative?
Because we wrote it down before. It was a sign of t, but this t is not t, but it's t minus t prime. Yes. So yeah, because I was too fast in writing it down. But what you should, if you write g as a function of 2 times, then everything will start depending on the difference of t's, and that's where the delta function appears. And this d tau is just this d tau appearing here. More questions? I killed you. This is just the beginning. Yeah, go ahead.
All these diagrams are for the average ones, right?
Yeah, because exactly. Yeah, everything is average over J, and the way we included this in the diagrams is like this dotted dashed line. And and here it is really important because depending on how you do the average, whether these diagrams contribute or do not contribute. So we are really taking the average over all possible J's here. Okay, 5 minutes and we continue.
Through the YouTube videos, it will be helpful. Thank you.
Okay. How is it you do this quite? Okay, so there was a nice way of getting the 2-point function in the large n limit by analyzing these Feynman diagrams, but it's not probably the cleanest one. You need to convince yourself that sum can be done and writing this renormalized propagator. So there's a very nice way of getting these Schwinger-Dyson equations by doing this path integral analysis. It's a bit long, but I think the calculation is more straightforward, and you just need to do the calculation that you have to do, and there's no doubt about what has to be done or what. And so I will kind of, well, because I'm well over time, I will sketch this calculation, try to convince you that this expression over here will simplify a lot in the large n, and that you can take there will be an n appearing in front of this action over here, and you can take the saddle point approximation and get the Schwinger-Dyson equations just from this path integral perspective. So what we are going to do is a path integral over this size, our Majorana fermions, over all i's at all possible times. So it will be some crazy measure. Then you will have to average over all possible realizations of the model. And we will put here ijkl, the distribution of these ijkls, j squared over n cubed. And then we will have e to the minus our SYK action, that is this thing over here. So that's it. And okay, we want to do this path integral or take it as far as we can. Path integrals are usually hard, so we'll do our best. But at least we have some guess coming from these Feynman diagrams that this path integral should simplify a lot in the large n limit.
Should the action equal minus some? Because you're subtracting off the no, as in the actual expression.
This one, you mean? I'm not sure. Okay, so the key observation is that we are taking these JIKLs from this Gaussian distribution. And so JIJKL only appears quadratically in all this sum. So it's exponential to something that is up to quadratic order. And so we can do this IJKL integral, JIJKL integral. Basically, we know something like this, minus ax squared plus bx is root pi over a e to the b squared over 4a. So here our a would be this thing over here, and b will be our sum over fermions. So if we do this, then I got rid of my integral over j's, and I only have an integral over fermions. And now, this kinetic term is still here, so let's put it. And now doing this integral gives me b squared. So I need to square this term over here. And so I will have the sum over ijk and L. I will have this a over here. This is a. Yeah, I will have 1 over a. So I will have 3j squared over n cubed. And then I will have my 2 copies this squared. So I have 2 integrals over time, d tau and d tau prime, of my 4 copies of the fermions. This is ijk. Well, okay, let's write it down. ijkl, ijkl. All these are at time t, and all these are at time t prime. And up to some numbers. I don't know, there are numbers all over. Okay, the next thing we need to see is that these fermions over here obey our anti-commutation relation. So I can start anti-commuting them to get one next to the other. And homework number 1000, check that this thing becomes, instead of sum over these 4 fermions, it just becomes a sum psi I only, with this at t prime, to the 4th power. So basically that you can group your fermions in this way. And okay, here comes the clever trick. So far we haven't done anything more than doing the integrals that we can. But now we will insert an identity somewhere. And that identity comes with this G and sigmas. So what do we want to do?
So
yeah.
sum direct was from 1 to 1.
Sum here?
No, in this last result.
This one?
Yeah.
I 1 to n, yes. Other questions? Okay, so the idea here is that I will be interested in computing this 2-point function. That is psi I, or 1 over n sum of psi I. And so the way to introduce this in the path integral is by inserting an identity that will have the form of a path integral over j of delta nj okay. I'm just imposing that G is whatever I want it to be. And then I will like to represent, well, here already we see that this G will start depending on 2 times. So this is tau and tau prime. And the other bilinear, our sigma, will appear as a Lagrange multiplier. So I will choose a representation of this delta. I don't have enough space. Let me write it down. So 1 will be dg, and now the sigma of E, let me write this properly, E to the minus n over 2, double integral of times. And now I will have sigma G minus psi. And you need to be a little bit careful because these are sums, and this is my new field sigma. You see that sigma just enters as a Lagrange multiplier that if you integrate it out, it imposes that G has to be our 2-point function. Okay, so now if I plug this identity in whatever I was writing before, I get that this thing is, so I still have my integral over fermions, path integral over fermions, but now I also have the G and the sigma, and now everything comes exponentiated because of the way I've written this delta function. The fermion, the kinetic term is still here, and then I have this double integral of n, well, let's put the n over here, sigma g minus psi psi plus j squared over n cubed. That's what I had before. Well, not quite, because now I will change this psi psi, sum of psi psi for whatever it is. So it's n times g. So I will have that this term over here becomes n to the fourth power times g to the fourth. So then I will have n to the fourth power here times g to the 4. Yeah, and some numbers. So you see again, these two cancel, and I start getting terms proportional to n all over. Yes.
Why don't you know n in the parentheses after you using sigma?
Here, yeah, there's an n that it's 1 over n. Some I was just trying not to write so much, but yes. Okay, and now written in this way, if we look at our psi dependence over here, now we have a term here that is quadratic in the fermions. Here there's also one sum over this over i's. So I have this term that is quadratic in the fermions, and there's another term over here that is also quadratic in the fermions. And terms that are e to the minus x squared, we know how to do these path integrals. For fermions, they are called Beresin. And Beresin Gaussian integrals is something you have an article in Wikipedia, so you can go there and see what's the result of that integral. And you will get basically that if you do path integral d psi of e to the minus, well, 1/2 of psi a psi, the result is a root of the determinant of a, where now a, well, we are looking at kind of a matrix. Okay, so let's do that integral and see what comes out of it. Let me erase all this now. So I'm doing this integral, so I still have an integral over g and an integral over sigma. I got as a result of the integration the determinant, whatever is multiplying the quadratic fermions. I have a dt over here. Let me write that as dt. And the other one is multiplied, where are the other? Here, by sigma. So dt minus sigma, determinant of this, to the n over 2. And then I have exponential of whatever is left, that is sigma g. Yes, so, but I need to write. Double integral over times dt d tau prime, sigma g. This comes from this term over here that doesn't have fermions, and the other one is this one over here, plus j squared g to the 4th. And now I can take this term into the exponential by doing exponential of log of the determinant. And so what I and when I take the log, I can take this n over 2 down here. And so what I end up having is this very nice expression that is a path integral over g and a path integral over sigma of e to the minus n over 2, I think, and an action of g and sigma. And this action will be so I sigma g will be just be log of the determinant of dt minus sigma plus double integral in times sigma g plus j square g to the 4th power. And this is great. We still have to do a double path integral over bilinear functions that can be quite hard to do in general, but we have an n appearing here in front of the action. And so when we take the limit of n going to infinity, we can just do a saddle point approximation and approximate, well, this action by its saddle point solutions. And so homework, again, verify that if you vary this action with respect to g and sigma, you get exactly the Schwinger-Dyson's equations. So g is equal to d tau minus sigma to the minus 1, and sigma is equal to j squared g cubed. The g part is easy because this term does not depend on g. So when you vary g, you just get sigma from here. Well, there's some minus that I'm missing somewhere, but well, okay, never mind. And when you vary from here, you get plus j squared g cubed. And the sigma one, you need to work out a little bit more because you have this log dead. You need to use some properties of these determinants, but believe me that you end up getting this. The other interesting comment is that if you, instead of doing the q equals 4 SYK, you do the q equals q SYK. Here, instead of getting a 3, you get q minus 1, but nothing else changes. Questions? So here you get these equations that are the same that we got from the Feynman diagrams, but we didn't have to start looking at diagram, which one contributes, which one doesn't. We just follow the path integral. We do as many integrals as we can. The trick is that fermions, if you look the integral smartly, you will see that they only appear quadratically, and then we can integrate the fermions out, and you get this effective action just for sigma and g. And quite nicely, n appears in front of the action, and so that means that it has a nice large n limit where we can just take saddle point solutions. And the equations, you just vary the action, and you get the equations of motion. And well, we end up with the same Schwinger-Dyson equations. Questions?
So it's kind of obvious to see where the G comes from compared to the other G that we introduced before, but the sigma
uses the background mode.
Yeah.
Is there a nice way to see that it is self-energy?
Yeah, I thought about that quite a few times. I never found a reasonable explanation. Here it just appears as a Lagrange multiplier, and yeah, somehow. I mean, after you do the computation, you can see that it's something like this from the equation, but when you insert this as a Lagrange multiplier in the path integral, yeah. Good question. Okay, so
maybe you get the same thing when you do it with a scalar field, and like many of the steps go about the same. So
yeah.
like lambda phi 4, you try to look at the phi bilinear.
Mhm.
Steps you did.
Yeah.
You get the same. So and that would yeah, then you can do a computation more easily. So you're like, yeah, it's not free.
Okay. So how much time we have till pizza is coming? 10 minutes. Okay. Let's do 10 more minutes and we stop whenever we have to stop. And so, yeah, this section was called solving the SYK model, but I haven't solved the SYK model. I got some equations that now I need to solve, but at least this sum, in the large n limit, they sum all the diagrams for any value of j. But I still need to find solutions to these equations. And so Kolya will show you numerical solutions. I want to insist a little bit more on the analytical part. So what do we have here? If I do some kind of arrow with the energies, or with J has units of energy. So at very high energies in the UV, I know, well, what I'm saying. So in the UV, I have J equals to 0. Yep. So sorry. And here I have free fermions. And here we said that the what is it? G, yeah, G is just d tau to -1 or something like that. D tau, yeah. And somehow we want to go into the IR. And we want to see what happens with the solution over here. In principle, we have the equations that will tell us what is going on over there.
How do you see the high energy phase?
How do you see?
And you say this comes from the solution of this.
Well, what is G? Well, I mean this. So, okay. So, what you need to look at is J. This thing is the dimensionless parameter. And so, yeah. This is in the line. Then we will talk about finite temperature maybe next time. And so the key step here is to see something that if you don't know it, you will never be able to see it. But so this term over here is a UV term that comes just from the kinetic part of the action. It's just the free comes from the free fermions. And so say that we want to go into the IR. So let's take this term out for a minute. And let's look at these equations. And these equations have a very nice symmetry. And maybe this will start to ring some bells from last class. So say that we take tau to some phi of tau. So we are just reparametrizing time. And so the key observation is to realize that if G and sigma scale in a very particular way, those equations are left invariant. And this particular way is, it looks like this. So this will go to the delta times G of phi of tau, phi prime of tau prime, and sigma delta q minus 1 sigma phi of t, phi prime, not phi prime, this is phi. This is phi prime, and this is, there we go. If G and sigma scale in this way, those equations over there are left invariant. And again, well, now even the first one is easy to see. So sigma gets lambda q to the minus 1. And then we have G that has q to the minus 1, but gets a delta from here. So both sides will have a term that goes like this to the q minus 1. So those will cancel, and this one over here will be invariant. And this one, how does it work? I think it works in the same way, but in order for this to be invariant, you will need to require that delta, I'm not sure, but I think it's delta equals to 1 over q. But again, homework.
Phi prime,
2 tau or tau prime, yeah. And this is nice because maybe you recognize that this is the way that conformal 2-point functions scale. So this means that when we went all the way, well, we strongly pushed our system into the IR by taking out a term that we know it's very, very UV. And in that limit, there's an emergent reparametrization symmetry that makes our functions G and sigma to scale as conformal 2-point functions. Of course, when we add this the tau term, that will break the symmetry quite explicitly. If you put again that reparametrizations in this equation, you will have an extra term that will not preserve it. So this symmetry will be explicitly broken when we insert this term. But nevertheless, it's still a symmetry in the deep IR of the theory. And this is quite nice because now we want to look for solutions. Say we are still in the IR. We want to find solutions that scale in this way. But we know which things scale in that way. They are conformal 2-point functions, so they have to be functions only of the difference, tau minus tau prime, that I will call tau over here. And there's nothing more that can appear over here that tau to the 2 delta and some coefficient. And the same with sigma. Well, it will be a different coefficient. And here sigma will scale like delta q minus 1, like this. And you can put back these solutions in here and find the precise coefficient. That's another part of the homework. And you can check that this delta is exactly 1 over q, or in this case, 1/4. And so this is nice because we solved the problem explicitly, analytically in the deep IR. And so now our solutions look more or less like this. So this is G as a function of, say, G tau. And so we've seen that when J is 0, the solution is constant. It's just 1/2 of sign. So we are always in positive time. So this is always 1/2. This is what happens for very small or 0 J. And when J gets infinitely, or JT become infinitely large, we know that these functions should decay as conformal 2-point functions. So they do something like this. And there's some interpolating thing over here that is the range where J tau is of order 1. Well, we don't have any, we don't have analytic handle at finite Q, but we can compare this with the functions that Collier is finding in his lecture that come from numerically solving this. Is there a question somewhere? Maybe.
We don't know these are solutions.
We don't know.
They're
So I'm not sure I understand the level. So under representation, if this is satisfied,
Yeah.
then the equations are
Mm-hmm.
What tells us that these transformations are valid? Are indeed the transformations?
No, you say, well, okay, if this is valid, then I know that these are left invariant.
Also, that's the thing that you were saying now, that these are not all the solutions.
Yeah, this is one solution that I can find by looking at the structure of these equations. I see that they have some conformal structure, so then I put an ansatz that is a conformal ansatz, and I check that these solutions are indeed solutions. So I found at least one set of solutions to my equations. Of course, there can be others, but Volodya is going to tell me that I'm out of time.
Some of them are.
Okay, so no, let me just recap a little bit and tell you where we are heading next, and then we finish. Okay, so we found some solutions that are conformal. We said that they are not all the solutions because in fact, I can reparameterize T to some phi of T. And in fact, yeah, if this phi of T is an SL2R transformation, this will leave my solution unchanged. And so once I found the solution, I break my symmetries from the full reparameterization to just SL2R transformations. And that's kind of the same pattern that was appearing last week in our JT analysis. And so the next thing I would like to do is to add back this delta tau term that I was throwing away and see what's the correction to these solutions that come from inserting back this delta tau term. And that's where the Schwarzian action will appear in our SYK analysis. So we started with some fermions in the UV with no interactions at all. We added this J that is an all-to-all coupling with random average. And we saw that that theory in the large n limit and in the deep IR, it had some conformal symmetry that was emerging in that particular limit. And next week, what we will do is to add back these corrections or the exact formulas and see that when we go a little bit away from the IR, the action or the effective action that rules that part of the system is the Schwarzian action, and it's the same Schwarzian action that was appearing last week in our JT theory. That's the idea. I was willing to do that today, but okay, it was a bit long. And the other thing I wanted to do is to consider the large Q limit and show you that in the large Q, these equations reduce to some partial differential equation that I can solve, and I can get a solution for any value of the coupling, including this area here where I couldn't get any analytic handle. So in the large Q limit, this system is completely solvable. And if I finish doing all that, then the last thing I would like to point out next week is how this is related to the idea of quantum chaos, and compute some 4-point function and see that it behaves in the same way that black holes do. All right, thank you. Sorry for being late. And, yep. There are more questions. I'm happy to answer them. Kings, people, don't leave without taking a picture.